We will have opening remarks from our four speakers, and then we will open up for question and answers. First up will be John Grunsfeld, NASA's Associate Administrator for Science here at Washington, NASA headquarters. Jim Green, the Director for Planetary Science Division at NASA headquarters. Jack Mustard, the Science Definition Team Chair and Professor of Geological Sciences at Brown University in Providence. And Lindy Elkins Tanton, the Science Definition Team member and Director of the Carnegie Institution for Sciences Department of Terrestrial Magnetism in Washington. And with that, I'll toss it over to John to kick us off.
Thank you very much, Dwayne. Very excited to be here today to talk to all of you in the press and other listeners about the results from our Science Definition Team for the Mars 2020 rover. For many folks last summer, it was an incredible ride through the Martian atmosphere, 7 minutes of terror to get Curiosity, the Mars Science Laboratory, on the surface of Mars. And in almost the year that Curiosity has been on Mars, it's been just an incredible drive, even though we're still on our way to Mount Sharp, in that we had a very fundamental question to answer, a question that has piqued the curiosity of astronomers and planetary scientists for quite a while. Of did Mars ever have an environment that was habitable for life? Does Mars have life on Mars now? And of course, we have many like the canals on Mars and who observed the seasons on Mars and those kind of things. And in the 1970s, when I was in high school, we sent the Viking landers to answer that question. And it was very, very exciting, very challenging. These were grand voyages, and Mars turned out to be what appeared to be somewhat lifeless. But the question still remained: did Mars ever have an environment that was potentially habitable for life? This was made even more exciting by the observations of Mars meteorites here on Earth, the Allen Hills 84001 meteorite of small structures that, could be something like primitive life. But still the question remains. And Curiosity has answered the question of whether Mars ever harbored a habitable environment. And that was kind of the prime mission, and I think that's just incredibly exciting. Now, we still don't have the context of when that was in Mars's history. When was it compared to the Earth's history? And that's what we hope to learn in the continuing voyages of Curiosity. We put together last year a Mars program planning group, even in the context of Curiosity, Mars Science Lab on the way to Mars, to try and look forward in time to what is the future of Mars exploration. Now, we already had MAVEN in the works, an atmospheric aeronomy mission, which will launch in November, a very exciting mission, soon to leave its fabrication point in Colorado on its way to space. And we also had dropped out of participation in the ESA ExoMars missions. And as part of the Mars Program Planning Group, we looked forward to what is the big picture plan for future Mars exploration. And coming out of that group, which was a group of NASA and community science members, they said that of all the options going forward, that the action really is still on the surface of Mars, with our Mars Reconnaissance Orbiter, our Mars Odyssey, and other spacecraft on their way to Mars, that we really needed to go back to the surface and do the next stage in answering the questions about potential past life on Mars. Did Mars ever have life? Now we know it had a habitable environment. So we put together, the Mars Program Planning Group, as I think many of you have followed, said, we recommend that you build another rover, that you model it after the Mars Science Laboratory, because the way that we engineered the Mars Science Laboratory enabled us to make another copy sometime in the future. All the engineering was captured, all of the drawings. In fact, we even have some spare parts. That would be the most cost-effective way to get new science to the surface of Mars. So we're still on the quest to answer the grand questions about, is there life somewhere in the universe other than on Earth? And this rover will get us that next step, is to go and analyze from the next step of, was there a habitable environment, transitioning from planetary science to astrobiology, to ask, do we see any evidence of past life in those habitable environments? So we formed a science definition team, gave them a charter, told them, what kind of mass, volume, and what kind of budget we might have to build scientific instruments. And it wasn't just science. It was more of a rover definition team, because we also included the Human Exploration and Operations Mission Directorate, Future Exploration for Mars, and our Space Technology Mission Directorate, Technology, looking forward to the next steps, not only in scientific exploration of Mars, but human exploration of Mars. Keeping in mind that all exploration of Mars is human exploration, because in the end, the science that we get is done by scientists here on Earth today and by scientists on Mars, hopefully in the not-too-distant future. So today, we're going to have you listen to members of the science definition team and instrument definition team on what the results were from their study. I think it's very exciting, because they do pose a potential suite of instruments that will help us answer some of these fundamental questions. The next steps after the science definition team is that here at NASA, we'll craft a announcement of opportunity for competitive selection. And I think that between the science instruments, the human exploration technology demonstrations, the space technology demonstrations, there's really an enormous amount of room for creativity and innovation and partnership that will allow us to send this next rover to Mars in 2020 that'll help us answer some of these cool questions. When Curiosity landed last August, I think it was as inspirational for kids today as the Apollo 11 landing was for me. Back then, kids loved dinosaurs in space. Today, kids love robots in space. And so I think this next step is going to be extraordinarily exciting and inspirational for the kids today who are going to be the scientists of tomorrow and their kids for the future. So with that, I'll turn it to Jim Green, the director of our Planetary Science Division.
Thank you very much, John. And of course, now that this report has been delivered and we've had an opportunity to analyze it and look at it, we are just delighted with it. It really fits well within our approach, our science strategy for Mars of seeking the signs of life. And in fact, it creates a very nice match set of missions over this next decade, for which it becomes the climax in 2020. We're going to be launching the MAVEN mission in November. It's an orbiter that will understand how Mars has interacted with the solar wind and lost its atmosphere. We then are partners with ESA on the Trace Gas Orbiter in 2016. And also, we will be landing InSight, which is a geophysical node telling us how active Mars is. Then ESA is leading a mission called ExoMars, which is a rover in 2018. And then at the end of this decade, Mars 2020, for which the science definition team has really carefully considered how this mission will support this decade's approach of science analysis on Mars, making a major step towards seeking signs of life. So what we have over this next 10 years is a very comprehensive set of international missions to Mars. Some we lead and some ESA leads, and it's just really quite the climax for our 2020 mission. As John mentioned, our next approach indeed would be to analyze the report, consider carefully all aspects of it, and then develop a call for instruments. And so with that, let me mention that it's my great thanks to all the members of the science definition team for all the very hard work that they've done. And I'd like to turn it over to the chair of that committee, Jack Mustard.
Thanks, Jim, and thanks, John. And it's been an exceptional pleasure to be part of this science definition team. To be involved with this group of really motivated and engaged scientists and engineers for the past 5.5 months has been truly inspiring. And this work that I'm representing today is testimony to their exceptional dedication. So I've not worked with a group that has been as dedicated and motivated previously. So that has been a great pleasure. But let me talk to you a little bit then about our process, how we arrived at our conclusions, and what we're passing forward to NASA. We began this process on January 24th, and over the next 5.5 months, I've never seen so many emails exchanged in such a condensed format. And this team met weekly via telecon and multiple times in between our group meetings to hash out the details that you will see in the 160-so page report, which I think will stand the test of time as a marker in our thought processes towards habitability, biosignatures, and how you explore a planet to seek signs of life. So if you look now at the first view graph that we have there on the web page, which is titled Seeking Signs of Past Life, the charter that NASA prepared for us had 4 primary objectives that we as a team worked our way through in a very methodical and enthusiastic fashion. The first objective was to explore an astrobiologically relevant ancient environment on Mars to decipher the geologic processes in history, including its past habitability. The second key objective was to assess the biosignature preservation potential within the selected geologic environment and search for potential biosignatures. And this is along these lines of seeking signs of life that Jim and John have spoken to. Our third objective, and this was pretty key, was to demonstrate significant technical progress towards the future return of scientifically selected, well-documented samples to Earth. And that is worded in a way that it could have a number of interpretations, but I'll tell you what our recommendation to NASA is for that. And the fourth objective was to provide an opportunity for contributed human flight and space technology program aspects of NASA for their participation, which is compatible with the science payload and the mission's payload objectives. So with those four objectives that were given to us in the charter, the science definition team, I think, has come up with an exceptional set of recommendations or guidance to NASA to think through. And so we are recommending that that the science definition team is recommending a mission concept for a science-focused, highly mobile rover to explore and investigate in detail a site on Mars that likely was once habitable. And our preferred mission concept employs new in situ science instrumentation in order to seek these signs of past life, had it been there. And I think it's really important that I convey to you and that you hear this, that we are not looking for the life that must have been there, because we don't know the answer to that question. But we're saying, given as many signs as we have had, including what Curiosity is finding, that there is promise that had life been there and had left a mark in the geologic record, we want to be able to seek those signs. And again, answer the question, had life been there, did it leave a mark? And then by investigating this site, we would look to the rover to select and store a compelling suite of samples in a returnable cache. And this would be demonstrate this enabling technology that is needed for the future science exploration. And the other aspects as well is to think about the enabling technology for future robotic and human exploration. Now, this mission concept, we believe, fully addresses these requirements that NASA put forward to us in the Science Definition Team Charter and is very well aligned with the recommendations of the National Academy of Sciences recent decadal survey report for planetary exploration. And we are very aware of a number of constraints, both scientific and fiscal, that went into this, and I think we worked very hard to come up with these set of fundamental conclusions that we have here. So those aspects are broadly represented in that first view graph, which shows the rover design, which is to use the chassis that the Curiosity rover uses, and there would be slight modifications to that to enable the science that we are proposing that this particular rover seeks to achieve. And we're representing that to you in a blueprint design because there will be modifications in the future. And as of now, the broad scope of the rover is defined. The details will need to be worked out as the mission evolves and develops. So now I want to move on to the second view graph chart that is on this web page here. And what this view graph is meant to show is the logic path by which we come up with one of our key recommendations, which is to develop, to carefully select samples that are well documented and to put them in a returnable cache to Earth. So as we talked through this, the first condition that we must think through is to understand, was there a past habitable environment? And MSL has shown the way by which one would make the measurements to come to that conclusion. Recognizing that you have a past habitable environment, what's the potential that, had there been biology there, that the record of its presence might have been preserved? And this is the notion of the potential for biosignature preservation. Because our best understanding of life on Mars, had there been life, is that the ancient record is the most promising area to explore for that question. And so we want to be looking for places where that record would have been captured and preserved. Having recognized, as we move now to the orange box, or yellow box, the third box in there, we could come to the point in an in situ rover exploration where we could define the existence of a potential biosignature. And our feeling is that to get to the next stage, a definitive biosignature, our understanding of what a definitive biosignature is and the instrumentation needed to do that is currently beyond the capabilities that we believe exist to the level of fidelity needed to convince the community of scientists about what a definitive biosignature is and its presence. So as we look on the path, as we go from the left to the right on this diagram, the science definition team was in absolute uniform opinion that those carefully identified sites with potential biosignatures would need to be returned to Earth in order to have the analyses in labs on Earth to get to meet the criteria to be definitive in that biosignature. Now, I should point out that the samples that one could collect to put in a returnable cache would address an enormous number of really important Mars science questions about the evolution of the planet, not only simply from a context of was it a habitable environment, but its igneous evolution and evolution as a habitable environment. So we feel it would address a significant number of key science questions for the future to come. So now I want to turn to what we think is one of the really important outcomes of the science definition team, which is what measurements that we proposed in order to achieve the objectives that I just laid out there to create a returnable cache and to assess the biosignature preservation potential and potential biosignatures. If you go to the third view graph or chart, what we have here is views from the Curiosity rover at 2 resolutions. And here I'll tell you that we are recommending that the 2020 rover has 6 measurement capabilities in order to move significantly along the science path that we've proposed. Those 6 measurement objectives are context imaging, such as shown in the slide on the left side of this slide, which shows a landscape acquired by the Mars Curiosity rover, which shows the distribution of rock and dust and the layers that we see there. So that would be the context imaging. We are proposing that this rover also includes context mineralogy, because mineralogy is really important in order to figure out the geologic evolution of a particular locality. And that is something that Curiosity does not have the capability to do, and that we're proposing that this rover would. Then we would move to the so we're talking about context mineralogy and context imaging. Then we would move to the idea of fine-scale mineralogy and fine-scale imaging. So for that, you can imagine we're moving to the right side of this third view graph, and we're getting to a closer view. And in the little white box on the right side of the right diagram, we see it focused in on a section of these rocks which have light-toned blebs, which are really interesting because from a habitability and biosignature point of view, that's representing, as the MSL team has shown, places where water has flown through cracks, and that could have been a place where biology could have taken up residence and left its mark. But we can't tell that definitively at the moment with our current instrumentation. So then we would say we need to go to a higher resolution here to probe why is there those particular components that we see on the surface. So if we go to the fourth view graph, here again is an image taken by the ChemCam imaging system, which shows a rock, which is a basaltic sedimentary rock, which has veins cutting through it. And those veins are incredibly interesting because, again, that shows water flowing through the system. And biology often takes up residence in these cracks and veins. And then the question would be, does that have the right signature, which would show that these were that there are biosignatures here and that they're well preserved? So here we would say we need to go to another level of observation, which is the fine-scale mineralogy and fine-scale imaging, and that is shown in the little box that's colored, which is showing, actually it's an image of a Mars meteorite, but it's showing the kind of resolution that we were proposing should be on this capable rover. And in this, the colors are representing different minerals which are showing up in this representation as if they're occupying those veins and cracks. And again, that would be a new capability that this rover would allow, the instruments that would hopefully be selected on this rover would allow the measurements to be made. So as we go from context mineralogy, context imaging, down to close-up mineralogy, close-up imaging, we're also recommending that the measurements include fine-scale chemistry, which is so important in order to understand the geologic processes. And the sixth measurement we're recommending is organic carbon detection. And this will be really important because we are proposing that the carbon detection be at the same scale as the representation of the fine-scale Martian meteorite that we're showing on the right. So to combine this suite of measurements would be an incredibly powerful set of tools, by which one would say, okay, as I now understand the geologic arrangements and the setup, I would know where I want to grab a sample from here. I have this carefully documented. I have an extraordinary amount of information. Then I would move on to the last view graph that I have here, and I would direct the rover to extract, to grind into that rock, but to maintain the spatial arrangement and distribution of components and preserve that in a core that I would put into a sample tube, seal that tube, and place that into a sample cache that would then be collected over the course of a mission. We have proposed that the capacity of that collection be on the order of 31 samples, which would be an extraordinary repository of science, a legacy for understanding the development of habitability on the planet, the biosignature potential, its preservation, and to be seeking those critical signs of life. So as these we believe to be some of the most important top-level results that have come out of our discussions and deliberations over the past 5 months. And as I'm going to step back a bit here and begin to wrap it up for the remarks that I wanted to make, is to say we are so excited on the part of the science definition team for this mission concept that we have worked hard with the engineers and other scientists over the past 5.5 months. I want to comment, in addition, that the opportunities to be working with the human flight component and the technology components within NASA to recommend two key components from that point of view. For the human flight component, there were a number of recommendations, including understanding the atmosphere at the final entry, descent, and landing phases, and to also be considering in situ resource utilization demonstration experiments. To me, this is way exciting because it says that this would be the way that we can cut the tether, so to speak, between the resources on the Earth and the ability to operate on another planet. And this is a very exciting addition to the capacity of this rover to make measurements and understanding. And the technology aspects that were also really important was to improve the landing site precision and accuracy so that we can get really, really close to these sites that we can recognize from orbit as being exceptionally promising from a habitability and biosignature preservation potential point of view. So as I said, I encourage you all to continue to read through this very short document that we've prepared. Well, it's the 160 or so page document, which is incredibly dense, but it's laden with the thought process that we took. I think it's very logically organized to arrive at the conclusions that we've had here. And what I want to do now is to sum up, as I have done here, sum up and to pass it over to Lindy, who will comment on some of the other aspects, maybe the broader implications of this mission for space science.
Fantastic, Jack. Thanks so much. The science definition team members worked really well together, and it's a pleasure to be here today talking about our report. We have a lot of optimism and excitement about what we're talking about here today. These 5 months of work with the team have been intense, and not just because of the many hours we put in or the approximately 6,000 emails we produced, but because of how important we all think the Mars 2020 concept is. So here's the bottom line. Questions drive science. But when it comes to NASA and the community together planning a flagship mission, the time and the commitment, the support needed, we should only be seeking to answer the very biggest questions. And one of the very biggest questions for all of humankind is, are we alone? And that is the question we're hoping to make really big advances with this Mars 2020 mission. Next, this recommended mission is in line with the conclusions, as Jack mentioned, the conclusions from the National Academy of Sciences Decadal Survey for Planetary Science. This document, the Decadal Survey, is the guiding document for our field, and itself the result of a tremendous amount of thought and work from the community. It's incredibly exciting and important that we're recommending this mission produce a cache of Martian samples that could be returned to Earth. And crucially, finally, NASA is not just about science questions. This mission is a beautiful platform to bring together human and robotic spaceflight goals. It's not just about science, and it's not just about human exploration. It's about inspiration. We would be inspiring a whole new global generation to think big, to aspire, and to reach out. With that in mind, let me pass this over to Dwayne Brown to start the Q&A.
Thank you, Lindy, and thanks for the speakers. Now, ladies and gentlemen, we're going to transition into the question and answer. We have a number of media on the call. I will toss it over to the operator to give you the instructions to queue yourself in. Please, we'll try to get to many reporters as we can, if you can have one question and a follow-up. So with that, operator.
Thank you, sir. At this time, if you would like to ask a question, please press star 1 on your telephone keypad. That's star 1 to ask the question. Please ensure your phone is unmuted and record your name at the prompt. One moment, please. Our first question comes from Irene Kloss with Reuters. Your line is open.
Hi, thanks very much. Thank you for the presentation. I had a couple of questions. I, of course, wasn't able to read through the whole report in the 45 minutes or so before this call, but I did kind of scan through and see what you all thought about the drill. It seems that, just off the top of my head, that's the biggest difference between the ExoMars mission and the mission you propose in 2020 as far as where to look for life. So I was wondering if maybe, Jack, if you could just comment about that a little bit. And then on a general sense, I don't want to put words in your mouth, but NASA has always been very careful to not call Curiosity a life detection mission. With the 2020 rover, would you say that you've now crossed that line and this actually is a search for life mission? Thanks.
Those are really good questions, and certainly let me address the first one first. We in the science definition team considered a number of ways to go about the exploration along the lines of what our charter specified what the objectives we should be directed towards. And we considered the aspect of drilling, and we felt about what are the resources that would needed to be able to address, to drill deep enough to address the kind of key questions. And the feeling was that to address the other aspects of it, we needed a nimble, mobile, flexible rover that could seek the signs of life in the detailed geologic record that would be present. And so given those objectives, then in addition to make significant progress towards sample return, our goal to create a returnable cache puts a lot of constraints on the resources available. And so in the trade space that we worked with, we decided to choose the flexible rover pathway upon which a drill was not technically feasible from our discussion point of view. And then the second point was about the, the second point, could you just repeat that?
Yes, just the distinction between the search for habitable environments, that is the kind of the baseline for MSL, and where you draw the line for this, if you actually would call this a life detection mission.
It's another exceptional question, and one that I think the community wrestles with on a daily basis. The feeling is that, from many points of view, that the planet's surface is quite inhospitable to life. And so to actually do an extant life exploration actually drives you to go to regions on the planet that are particularly challenging to potentially access. Plus, our capabilities to look for that signature means that you're making assumptions about the nature of that life in the context of Earth life. What if it is not in that realm? And that the exceptional characteristics of the surface being quite inhospitable to life may lead the community or broad section to think that the best prospect to look for the past signs of life or the signs of life would be in the ancient geologic record. So that's where it drove us in that direction.
Our next question comes from Gina Superi with ABC News. Your line is open.
Yes, when you talk about sample return, how do you anticipate that working?
So when we talk about sample return from what the science definition team worked from, our objective was to do the first step towards what a sample return would be, which is to create a returnable cache. I would then say that what happens next would be that cache is returnable at a future date, and I would turn the follow-up to that question over to Jim and or John to say what do we do with that in subsequent time frames.
Thanks, Jack and Gina. So we didn't talk about the marching instructions we gave to the science definition team, but one of them was, that we wanted to be responsive to the planetary decadal survey priorities, the top of which was Mars sample return. And so we asked the science definition team to come back with an answer or report that makes significant progress towards Mars sample return. And it's detailed in the report, but the report says that getting samples back here on Earth gives us the highest capability to understand the science that's contained in whatever samples are brought back. And so the 2020 rover had to make significant progress towards that eventual goal. And so the sample acquisition, the coring, drilling, coring, the sample handling, was a very important part of that. And in the process, the science definition team found that going that next step of putting the samples into a returnable cache is a small step forward as part of the whole ensemble of equipment, but it doesn't address the actual sample return. So this is the sample acquisition, very importantly the characterization to determine that you get the samples that you want. That's really the crucial step. And then encapsulating them into a cache. At this point, we haven't gone, in the forward planning the next 10, 20 years or so, to show how we would then acquire that cache and return it to Earth, although we've done a number of studies in that direction. But really we're stopping at the point of doing the technology development and demonstrating that we can find the samples that we really want, and the context is everything. The making sure you have the right sample is everything, and then getting it into a cache. A lot of considerations go in there, including planetary protection. We have to consider about bringing samples back from Earth. How do we protect, life on Earth from anything that might be on Mars? But also, we want to be able to make sure that in that returnable cache, that the system that eventually will go acquire that cache and bring it back to Earth doesn't, change the cache in any way. It doesn't, threaten, the integrity of the samples, for instance. And so that's all forward work. It's something that we'll continue to look at. I wouldn't, this is, John Grunsfeld, the astronaut, speaking. I wouldn't rule out that perhaps human explorers will go and retrieve the cache, in 20 plus years from now, as explorers, set foot on Mars. That's an eventual goal, is to put astrobiologists and planetary scientists on the surface of Mars. Of course, they'll bring back many more samples as well, but that's still forward work.
John, if I may also, this is Jim Green, add a couple things from my perspective, too, and that is, building on curiosity was really an essential element of the 2020 mission. I think one of the most exciting times I had in watching Curiosity, besides the 7 minutes of terror, was when the drill penetrated the rock and we saw gray Mars, not red Mars, but gray Mars. Now that drill powders up material, doesn't keep the geological record intact, but it gives us the exciting glimpse that past Mars was completely different than what it is today. So this means this rover, with the ability for the instruments to interrogate samples and to really look into that past, not just to hang on to them in some caches, if you would drill into rock and then cache it. That's a sideline, as John mentioned. The interrogation and the analysis that leads us to those important cores is what really makes this mission so exciting a step forward in seeking signs of past life on Mars.
Our next question comes from Alan Boyle with NBC News. Your line is open.
Hi, thank you for taking the questions. I think John addressed what I was hoping to find out about the schedule, that the schedule for the actual sample return is still to be determined, that this is an initial step, but the planning for what to do with those samples is still a question mark. Has there been any discussion by the team or by NASA about how international partners might mesh with this exploration plan?
Yeah, perfect lead in, and I had meant to add that even on the Mars 2020 rover, we are open to international participation. As you know, virtually every mission we've done in the science arena at NASA is an international partnership, and certainly virtually all of our Mars exploration, including the Curiosity rover, has significant international participation. And so, we've already been in some preliminary discussions. This is the rollout of the science definition team results, so we haven't been able to talk specifically with our international partners, but we're certainly very open to ideas both on the 2020 rover, but also, in how we'll work going forward. Just as, we're a team member on the 2016 and 28 ESA ExoMars program as minority team members, we hope that we'll continue to be partners with ESA and our other international partners going forward with this mission and potentially for the sample return.
But in terms of schedule for actually returning the samples, it could be the 2020s, it could be the 2030s. It's to be determined. Yep,
that's to be determined. And in fact, if you look at the Vision and Voyage's decadal survey, Planetary Science Decadal Survey, they specifically cite 2020s or 2030s for the sample return mission that they proposed, and we're now, a few years beyond that. And so I think that's the time frame that the scientific community was already willing to accept, and that, we should expect. I think the 2020s is probably ambitious, but we're very ambitious here.
Yeah, and as John points out, the way ESA now is aggressively approaching Mars with their trace gas orbiter in 16, followed up by their own rover system, ExoMars, in 18, really makes them an outstanding partner for future Mars exploration, and will be an important element in terms of how samples may be able to be brought back.
Our next question comes from Keith Cowing with NASAWatch.com. The line is open.
Yeah, this is Keith Cowing from NASAWatch.com. I'm going to frame these questions as I have before as a biologist who read these documents. I actually got to the astrobiology part right away, but I've been reading these things for 30-some-odd years. And, you know, it's sort of like you talk about inspiration. This is John Grunsfeld. And yet, it's sort of like you bring people right up to the big question, but you wimp out before you actually say, well, is there current life on Mars? And it's sort of like a litany of things of how hard it is to do, therefore you're not going to try. And yet many of the assays that you're going to be doing looking for biosignatures could be relevant to things that could have been there yesterday afternoon, so to speak. So, first of all, how can you explain to people that after 50 years between the design of Viking and the operations of Mars 2020, NASA is afraid to ask that big question again, or hasn't figured out in a half a century of being on Mars how to ask that question, especially given the amazing, astonishing advances in biotech and miniaturization. And second, to piggyback on this, and you brought this up, if you're going to send these rovers at this every 2-year thing, at the pace at which you're slowly getting asymptotically close to that question, it's going to be almost butting up against the 2030 time frame when humans are going to go to Mars. And you just said yourself that humans may go pick up the samples the rover collected. Well, isn't that sort of bass-backwards? Wouldn't you want at least some of these big questions about life to at least have been attempted so as to inform how you would do these missions? Sending a sample return mission, the precursor to Mars, to have people pick it up, it's sort of a waste of money.
So I'm not sure which one to answer first, but let me answer your first question first, which is, we pose to the science definition team to do, the scientifically traceable best effort at moving from a planetary science mission to an astrobiology mission. And they've done a stunning job, and what they have proposed is a suite of measurements for the most likely case, that Mars, when it had a habitable environment, there may have been some preservation, if there was ever life on Mars, some preservation in the rock record, and we should go after trying to find that. And so that's the astrobiological context of looking for signs of past life on Mars. And that's judged the most likely case if during that period when Mars was habitable in the way that life is habitable here on Earth, that it might have been preserved. Now that said, if you bring instrumentation which has essentially a very high-power microscope that can see features that are, microns in extent in the grains, if there is extant life on Mars, microbial life, say, you might have a chance of seeing some kind of structures associated with that. And science proceeds in a stepwise manner. The other part is that as in opening up space for technology demonstrations, we certainly are open to the idea that people could propose, and it's in part of the science definition team report, which I just got a copy of as well. But if someone wanted to propose some kind of life detection experiment that would, for instance, measure how much Earth life we bring with us, even though we try and do forward planetary protection and sterilization to a very high degree, ultimately some contamination does arrive on Mars, and we'd want to be able to do some assessment of what level does that survive, the long trip to Mars, the descent to the surface and the surface, and if extent life existed on Mars, which we still think is somewhat unlikely, and if it had the same kind of characteristics as life on Earth, that kind of a system might detect it too. So we're open to the idea, that somebody could propose such a thing, and then it would be up to the competitive processes to decide if, given the cost, weight, and volume, that could outcompete the other ideas that are presented. So I don't think we're excluding that. As far as the time scale, we're sending something that given our fiscal ability to mount a mission at all and to procure instruments and the competitive selection is the best that we can do. We currently don't have a specific roadmap for when we're going to send people, NASA, to send people to Mars to land on the surface. And so, my tongue-in-cheek comment about, who knows, maybe the people will go pick up the samples is because we also haven't laid out a roadmap for how we would return cacheable samples. We've certainly done a number of studies, and, I would like to see it be a kind of race because I really want to see scientists on the surface of Mars. It's, probably more likely that we figure out a way to do sample return robotically first, because that demonstration of sending a spacecraft to Mars, acquiring samples, launching it off the surface, and bringing it back shows that we can send things to Mars and bring stuff back, which would be, a definite plus if you were sending people to know that at least we've demonstrated on a small scale that we can send things there and bring them back, assuming that the people you send you want to bring back. That's all in the forward planning. So it's a reasonable question, but we don't have a requirement that we bring samples back before we send people. That's not a specific requirement that we're carrying, other than some discussions about protection of planet Earth. So I think what I'd like to do is hand it over to Jack to talk about the deliberations that the STT did on this very specific question that you asked of shouldn't we just send an extant life detection experiment.
Sure, and that is a, you can say there is an ongoing debate within the planetary science community, and I would say that we have absolutely, so we work on facts or evidence-based exploration, and evidence-based science is what we tend to work with. And to date, the evidence that we have from observations of Mars and Martian samples is that we don't have the clear indications that life is at such an abundance on the planet that we could go there with a simple experiment like Viking and detect that there. So then we think about what are the steps that we would go to address the question that Lindy put out there, which is the big question, are we alone? And to go and look for simple organisms or not so simple organisms that are living within that toxic, harsh environment, we just think is a foolish investment of the technology at this time. But to be thinking about that Mars in its past had these habitable environments, as MSL showed, had the right aqueous chemistry, the right temperatures, the right benign characteristics, where should there have been microbial life, it could have actually done very well. How would that leave a record to show that it may have existed? Because what you really want to get at is, was there ever life elsewhere? Was there a second Genesis? Did that have the same characteristics as what we had on Earth? And to go after those questions, we want to be, as John was saying, is you want to approach it in a logical, systematic, stepwise fashion so that you can be confident about your results as you move forward. And to the best evidence that a good segment of the planetary science community understands, that period of time on Mars was in its ancient past, when habitable environments were common and plenty, and have left a number of records which we can see from orbit, and we would like to sample those to see if it left the biosignatures. If that biosignature happens to be a dinosaur-type bone, we probably wouldn't need to have to return that sample. We could recognize that from our current capabilities. But our understanding is that it's likely to be microbial, and that's a darn hard measurement to make, and a darn hard measurement to convince the skeptical science community, because scientists are naturally skeptical, that is indeed the case. So the science definition team wrestled with this question, and there were certainly those who pushed the question, well, shouldn't we be doing extant life? But the feeling was, on the basis of the scientific evidence we have today, that the most logical steps forward were to look for the ancient signs of life that would be preserved within the rock record. And I think if you get to that part of the report to think about biosignature preservations, I'm really proud of that part of our report from the astrobiologists on the team and the rest of the team who laid out a really beautiful strategy where one could approach it from a 6-axis chart, so to speak, to think about the 6 ways that biosignatures could be developed, preserved, and recognized, so that we're not saying, let's go for the one thing that says there was life. Let's look at the assemblage of evidence needed to put forward to build a case that there may have been evidence of that type of process, a biological process on another planet. That is a big question, and we wanted to approach it from a rigorous, scientifically based point of view.
If I could just add to that and really underscore what Jack is saying, it's not just the instrumentation and the basis of the science, but it's also a matter of maximizing potential return. If we were only looking for what microbes could be found on the surface in this place right now, that's like a tiny snapshot of the history of Mars and the possibility of life. But if we look back through the rock record, we're basically integrating over time and maximizing our chances of finding results.
Our next question comes from Frank Mooring with Aviation Week. Your line is open.
Thank you. I have 2 questions. One has to do with targeting your landing site. Do you go back to the sites that may not have been, that weren't picked for curiosity, or are there other criteria that would be better for this type of mission? And then also, maybe just to continue the discussion that we've just had, is there any relatively simple way to tell what the difference is between characterizing a promising sample and actually defining life as you might be able to do it, or evidence of past life as you might be able to do it back here on Earth? What can you do here that you can't do there?
Okay, those are excellent questions, as all the questions have been, I should add. So landing sites, that is one of the aspects that we devote a section of our report to that. I think it's Chapter 7, in which we look very carefully at the aspect of landing sites. And we entered that with the basis upon which the landing sites have been selected for the Mars exploration rovers and for Curiosity. And that process has worked exceptionally well for both identifying sites that fit within the landing capabilities of whatever spacecraft is going, and then the level of scrutiny that is brought to bear to those sites on the basis of the orbital data to really hash out how that site may or may not fit the objectives of that mission. So for 2020, the objectives of that mission are different than MSL, are different than the Mars exploration rovers, are different than what ExoMars will be going through in its process. The thinking of the SDT is one in which we would recommend to NASA to pursue a similar process it used for the MSL, to ask the community to propose their best sites that fit the objectives of the mission, and to let the scientific process take hold, and to have the exceptional discourse and discussions that go towards the selection of the landing sites. And I would say every landing site that was part of the MSL and every landing site that has been considered for MER and other places are back on the table, so to speak, and including the current landing site. And if it stands up to the test of scientific scrutiny to meet the science objectives, it would rise to the top. So I would say what's exciting is that the technology that we're suggesting that NASA pursue would actually enable even finer scale landing ellipses to really get at some absolutely, from what we can see from orbit, pretty intriguing places. So I really look forward to that process as it moves forward. And then the question about the life detection part of it, to pursue it a little bit more, to say that the type of the detection of life as we know it on the Earth, to actually send the assay capabilities that we have on Earth to Mars, actually is a challenging in and of itself. Just saying we're going to go and understand life as we know it, but then to think about, could we imagine looking for life that may have evolved a different pathway, in some ways could be it's not as well based as we would hope. So what the SDT put forward there, and in the aspect of how to recognize biosignatures, how to assess whether they could have been preserved, and then how you would understand the geologic context by which you would select the samples and bring it back, is important. So what we can do with the samples in Earth labs is just several orders of magnitude above what you could do with a sample on Mars with instruments that you would build to be space qualified and to be able to handle the samples in a way to get at the fine precision necessary. So what I like to use is the example of the meteorite ALH 84001, which in 1996 Dave McKay and colleagues proposed had 4 lines of evidence that showed that this sample had a habitable environment in which actually there was preserved biosignatures. And to this day, the 15 years of intense scrutiny of that rock subsequent to Dave McKay's announcement showed that 3 of those lines of evidence proved not to be well supported, and the 4th line, which is that there were mineral structures that could have been produced by biology, I guess I wouldn't say is completely closed, but it is a very difficult set of measurements to make. If we then move into the next level of analysis is to get at the organic detection, which the Mars Science Laboratory has the capability to do organic detection, and we're really enthusiastic that as it moves into the Mount Sharp environments, it will be able to make the kind of measurements to show that organic compounds perhaps do exist on Mars. At the present state, we do not know that the types of organic compounds necessary to assess those level of questions we're not yet convinced of. But if you have those samples back on Earth, you can do sequential analysis, you can do repeat analysis, you can use instrumentation that, as of today, is not flight qualified, and that just gives us the level of scrutiny and capability that is going to be required to go after the biosignature and definitive biosignature characterization.
Our next question comes from Todd Halverson with Florida Today. Your line is open.
Thanks very much, Todd Halverson of Florida Today. I think for John Grunsfeld. I was wondering what the cost constraint was that you put on the SDT in terms of, dollars. I'm looking for a dollar figure. And I was also wondering how you go forward from this point now that you have this report in your hands. Thanks.
Todd, this is Dwayne. I'm going to have ask Jim Green to answer. John got called upstairs. He's going to be right back, so go ahead, Jim.
Okay, great. Yeah, indeed. When we started out with this process, we analyzed, indeed, how much infrastructure we had that we could leverage with the Curiosity EDL and the chassis and the basic elements of the rover. And since we saved the prints and updated them, we will realize a major cost savings. So we're looking at an mission with an approximate dollar amount of about $1.5 billion, excluding the cost of the launch vehicle, which would be on top of that. So backing up and seeing then the available funding of about $100 million, $80 to $100 million for the instrumentation was an element of the science definition team's challenge to be able to outfit the rover. And the second question is, where do we go from here? As I mentioned in my introductory remarks, we will be analyzing the report in much more detail, and from that we will begin the process of developing an announcement of opportunity for instruments. In other words, an open call, an open competition to the community that satisfies the requirements for the measurements and analysis of the samples and then the caching. So That we anticipate will take us several months to do, but we're going to work on it aggressively and get it done hopefully by late fall.
Next question comes from Mike Wall with Space.com. Your line is open.
Yeah, thanks guys for actually doing this. I just had a question. I mean, obviously you guys don't know what the instruments are going to be or anything, but I was just wondering, I mean, all of these science goals, is there anything that really jumps out as being particularly challenging, or that will require any kind of technological leaps? I mean, for example, all of this coring, and that's going to require some new technology that you haven't used on the surface of another world yet. So yeah, could you just go into detail about what some of the biggest kind of challenges might be meeting these goals going forward?
So this is Jack Mustard. I'll start the response to that question. What is the new measurements? What are the new technologies that would be required on this mission that haven't previously been done? And I would certainly say the coring system is one that has had a lot of development within the engineering laboratories here on Earth, but has not been implemented for a spacecraft mission, and so that would be a significant new technology to be brought to bear. Some of the other measurements, when you talked about the instruments, what are the new measurements that we're talking about? This is potentially a really, really exciting aspect of what NASA can do with this mission, is that we on the SDT proposed broad measurements, such as fine-scale mineralogy. And that is one that there are some really promising technologies that have been developed in the laboratories to be able to measure mineralogy at the scales I showed in the view graphs of really detailed mineralogy and chemistry together. And that would require a new type of spacecraft instruments that haven't been flown yet in this kind of environment. To be able to get that technology up and running, in place, to be coordinated with our context geology and context mineralogy will be an important step forward. And the third one is the idea of this carbon compound detection, which the SAM instrument on the Mars Science Laboratory certainly has the capability for the carbon compound detection through the powdered samples that are generated through the drill and brought into the system. What is different about what our measurement, potentially different, it will really depend on what the instrument competition brings out from the community. But what is different there is that we would be looking at carbon compounds as they sit in the particular geologic environment that they're recognized in versus those that have been ground up and you've lost the context. And that would be an important new direction within the measurement objectives.
Ladies and gentlemen, this is Dwayne Brown. We are running overtime here, and we're probably going to be able to only last another 5 minutes before we're going to have to end the call. What I'm going to do here is we're going to take 3 more media. If you can give us one question, and we'll try to give you quick answers, and I'll leave some information for you all who don't get a chance to ask a question to get in touch directly with Jack, and of course you can send me an email and I can get those answers to you with the respective folks. So operator, if we can take 3 more calls, and then we'll have to sign off shortly.
Thank you, sir. Our next question comes from Lisa Grossman with New Scientist. Your line is open.
Hi, thanks for taking my question. When they were talking about doing a cache for sample return on MSL, there's some worries that the rover wouldn't go to some interesting places because it had this backpack full of really valuable rocks. And so for this rover, which is going to be based on MSL, I was wondering how you get around those same concerns where you wouldn't want to send the rover into the most interesting environments because you would not be able to get it back.
Oh, okay, Lisa, thanks for that question. And one of the problems in talking to scientists, when you ask us questions, we want to keep talking. But I'll try and make that brief.
Okay.
I'll try and make my answer brief. That is a really important question. You can look at what happened with the Mars Exploration Rover when they were poised on the rim of the particular crater, and they had to make the decision: do we go in and maybe not get out, or not, or we just stay outside and explore our environment there. I think that's going to be a really important set of questions that the science team of the rover that will be selected future will be wrestling with, and then certainly in the higher levels of NASA will be in close communication, because ultimately you would want to be able to return whatever cash you have, and you don't want to left in a place where that's not possible. So I think that's going to be a trade space to be explored in the future.
All right, thank you.
Our next question comes from Adam Mann with Wired. Your line is open.
Yeah, hi guys. I guess I'm just wondering, given that sample return is, this would be sort of the first part of sample return, how much this commits NASA to doing the next parts in what sort of time frame, and what sort of assurances you guys can give to planetary scientists who are not interested in Mars, that they will still have big flagship missions as well.
Well, this is sample acquisition and caching. Clearly, to do sample return, you have to send something else to Mars that has an ascent vehicle and a return vehicle, and then a way to get it, safely to laboratories on Earth. And the only thing that we're committing to is that we're sending, this very capable scientific rover to Mars to try and answer the questions that you've heard about in the last few minutes, and that will, have the capability of putting samples into a returnable cache. So we're not signing up to a timetable or, commitment for a follow-on mission. That's future work, as we go through the rest of this decade. And it's very likely that, we'll pursue other planetary objectives besides Mars before we get to a mission to acquire these samples or other samples that may be acquired by other missions. Hard to say. It could be that this rover lands in what looks like a really exciting place, and we acquire some very interesting-looking samples, but decide that we don't want to return these samples. That's all still in the trade space. There's a certain amount of scientific luck involved. It could be that we in 2022 pick up a sample that looks really interesting, and we decide we ought to go get these samples. So I think that's all open in the trade space, and I also wouldn't rule out that even before we get there in 2021, that Curiosity discovers something interesting that helps us decide where we're going to go with this rover, talking about landing sites. So all of that's future work, and I think the more important question is, what does the U.S. budget look like for the future of any planetary missions?
So this Jim Green, just very briefly, of course, we have our Discovery program, our New Frontiers program, very focused missions. Our next New Frontiers mission, OSIRIS-REx, is also a sample return. It's going to an asteroid, very important, a Type C carbonaceous chondrite. So we're going to continue to be as aggressive as possible in a balanced program as recommended by the Planetary Decadal. Yes, this is a large mission. Maybe the only large mission we do in this decade, but we will continue to have many more missions in our other calls.
And our last question comes from Leonard David with the AIAA, Aerospace America. Your line is open.
Hey, thanks a lot. Unfortunately, I probably have 25 questions. I'm trying to hone this down to probably the basic thing in regards to life. Mars is a has-been planet, or it is now a place for life. As I collect my Social Security checks here, I lived through Viking, and I'm not sure I agree with Jack on simplicity of the life science detection experiments back then. They did the best they could. But we're still grappling with this question. I guess if I have to clear away the 20 questions, it's really, can't we sterilize this spacecraft and let's move on to the question that we need to answer? And that answer, and this gets into the scientific side, the life on Mars question and answering it may have nothing to do with are we alone? Because of the proximity of the planets and cross-sterilization, we may be getting a bogus answer to a question that we've spent billions looking for.
Well, this is Jim Green. From a planetary science perspective, the origin and evolution of our solar system with material that is, organic material that we see in our comets and our outer part of our region is incredibly important. But you have to recognize our whole local group of stars was formed from that region. We've literally shared spit with material in our whole local group in our outer parts of our solar system. And so consequently, the conditions and the building blocks of life, the questions on how life originated in our solar system will be some of the same basic questions that will be important and relevant for every of the other stars in our local group, and therefore throughout the galaxy. So it's a huge leap that we're making, for which our first step within our solar system of understanding if life has existed elsewhere beyond Earth is indeed an extremely important one.
And this is Dwayne Brown, ladies and gentlemen. Before I give it back to John Grunsfeld for some final remarks, I again want to apologize. Please, Leonard, if you have your 20 questions, I can get you in touch with anyone on the panel. Just send me an email. For folks who want to get in touch with Jack, you can call him at 401-863-1264. That's 401-863-1264. He will get back to you as soon as he can. And again, my apologies, but we will be able to get to your follow-up calls. With that, John, you can close us out here.
Sure. Well, Leonard, thanks for that final comment, because it really, again, poses the grand question that we're not just trying to answer on Mars. We're also, trying to answer the question of, are we alone in the universe using other means? The James Webb Space Telescope is another example. It's an infrared telescope that can look at the content of molecular clouds, and we'll be able to do planetary atmospheres around nearby stars. And so we are rapidly, approaching, with our technology, the ability to answer these things. However, we talk about, Curiosity and our other Mars exploits and Viking, and we talk about James Webb Space Telescope or Hubble or, Juno on its, way to Jupiter. These are all really hard missions. And, the work that we're doing in preparing ideas for a possible complement of instruments on a 2020 rover, this is in some ways the easier part. But even that's not easy. And so along those lines, getting a group of scientists and engineers to agree is also really hard. So I want to extend my thanks to Jack Mustard and the entire instrument science definition team and all the folks here at NASA that have worked so hard to get us to this next step of being poised to release an announcement of opportunity for instruments. And we still have, 7 years of really hard work ahead of us. In difficult funding times, and we're, the team at JPL is already out and running on developing, the engineering and procuring the long lead time items for this 2020 rover. So this is just one chapter in a long story of our exploration of Mars, that really started in a serious way with the Viking landers, and as you said, Leonard, is a continuing story, and it's going to be very hard to get to the bottom of it, even when we send human explorers who can bring with them better tools and techniques. And, I sincerely hope that this is one step on the way to that path. Thank you all very much for participating. Send your questions in, and we look forward to the next opportunity to interact with you all and tell you the next bit of this story.
That concludes today's conference. Thank you for your participation. You may disconnect at this time. One moment.